Imagine holding in your hand the fundamental building block of space-time itself. Not an atom, not a quark, but something far more elusive. A particle that might not even exist. For a century, physicists have been hunting for the graviton, a quantum ghost that could finally unite our two greatest theories of nature into one master theory of everything. But here's the twist. We've spent decades building theories around something we've never detected, and some of the brightest minds in physics are starting to wonder if we'd been chasing a phantom. What if everything we thought we knew about unifying the forces of nature has been based on a beautiful mistake? Today, we're diving deep into one of physics' most profound mysteries. By the end, you'll understand why the existence or non-existence of this single particle could reshape our entire understanding of reality. The story of the graviton begins with a revolution that changed everything we thought we knew about reality. When Max Planck first suggested, and Albert Einstein later proved, that light is made of particles called photons, they opened a door to an entirely new way of understanding the universe. This wasn't just a small adjustment to classical physics, it was a complete reimagining of how forces work at the most fundamental level. Think about what this discovery really meant. Light, which we experience as a smooth, continuous wave, is actually made up of discrete packets of energy. The electromagnetic field, which extends throughout all of space, isn't truly continuous at all. It's quantized, broken into countless tiny chunks that we call photons. This realization set physics on a path that would dominate the next 100 years. As quantum mechanics evolved into the more sophisticated framework of quantum field theory, physicists discovered that this particle-based description wasn't unique to electromagnetism. The weak force, which governs radioactive decay, has its own mediating particles called W and Z bosons. The strong force, which holds atomic nuclei together, is mediated by particles called gluons. 3 of the 4 fundamental forces of nature, each communicated by their own particles, each following the elegant rules of quantum field theory. But there's a conspicuous absence in this picture. Gravity, the force we experience most directly in our everyday lives, stands alone without a known mediating particle. For a century now, much of theoretical physics has been built on the assumption that if we could just figure out the graviton, the quantum particle of gravity, we would finally have unified all the forces of nature and be on track to a theory of everything. The graviton has become the holy grail of particle physics, the missing piece that would complete the puzzle.
But here's where things get interesting, and perhaps a bit uncomfortable for modern physics. We're now a full century after the birth of quantum mechanics, and despite enormous effort and brilliant minds dedicated to the problem, we still have no direct evidence that the graviton exists. Much of our work in unifying our theories hinges entirely on its existence. If the graviton doesn't exist, if gravity fundamentally works differently than the other forces, then much of that century of work may have been pointing in the wrong direction.
To understand why the graviton matters so much, we need to appreciate just how different our two great theories of nature really are. Nearly the entire universe can be described using just 2 frameworks, quantum mechanics and general relativity. But these theories look wildly, almost incomprehensibly different from each other. On the quantum side, we have fields filling all of space. These aren't simple things, they're dynamic entities whose oscillations give us all the known particles of matter and 3 of the 4 fundamental forces. These quantum fields have a strange property. They fracture into discrete shards as you zoom in closer and closer. Nothing in the quantum world can be pinned down precisely. Everything exists in a state of fundamental uncertainty, with particles popping in and out of existence,
their properties defined only probabilistically.
On the relativity side, we have something entirely different. Space and time aren't separate entities, they merge into a unified fabric called spacetime. This fabric isn't rigid. It can expand, contract, warp, and bend. It stretches in response to matter and energy, and this stretching, this curvature of spacetime itself, is what we experience as the force of gravity. It's an elegant picture. Matter tells spacetime how to curve, and spacetime tells matter how to move.
This division of labor actually works remarkably well. Quantum theory gives us the stuff of the universe, all the particles and forces. Relativity gives us the container, the stage on which everything plays out. Matter exists in space-time. The quantum fields operate within the framework of curved space-time. So if this picture works so well in describing the universe, why do we need to try to force gravity to work the same way as the quantum forces?
Partly, it's about aesthetics and our deep intuition about how nature should work. We expect, or at least hope, that all the complexity we observe in the universe emerges from unified underlying laws. That proved to be true of all matter and most of the forces of nature, quantum fields all the way down. It would be genuinely strange if the most fundamental layer of reality was actually two completely unrelated things, and extra strange if the theories describing those things are profoundly different, fundamentally discrete and random for the quantum world, fundamentally continuous and deterministic for relativity.
But maybe that's just how it is. Maybe the universe doesn't care about our aesthetic preferences for unified, elegant theories. Maybe reality at its deepest level genuinely is two different things operating by two different sets of rules. That's an uncomfortable thought for physicists, but discomfort isn't an argument.
There's another reason besides aesthetics that we need these theories to connect, and this one is more compelling. At a fundamental level, quantum mechanics and general relativity actively contradict each other. Together, they describe most of the universe beautifully, but in certain extreme places, like the center of a black hole or at the Big Bang itself, they generate contradictions and paradoxes. The equations break down. They give us infinite answers or no answers at all. It seems that these contradictions can only be solved by finding the master theory in which quantum mechanics and general relativity connect seamlessly.
For various reasons, most physicists trying to solve this problem have followed a particular path, the path of particles. They try to quantize gravity just as they once quantized electromagnetism. And this search for a theory of quantum gravity naturally implies a particle that mediates gravity, the graviton. If the graviton exists, then gravity has to be quantum. If gravity is quantum, then the graviton has to exist. These two ideas are inseparably linked.
Let's understand how this quantization process works by looking at how we got the photon. We start with the classical electromagnetic field, the one described by Maxwell's elegant equations. A field, in this context, is just something that extends through space and has some value at each point. That value could be simple, like the temperature of air in a room, giving you a temperature field. Or it could be more complex, like a vector with both magnitude and direction. The electromagnetic field is like that. It has both a strength and a direction at every point in space.
Fields can support waves, oscillations in field strength that move through space. The density field in air supports sound waves. The electromagnetic field supports electromagnetic waves, which we know as light. So when Planck and Einstein showed that light is made up of indivisible particles, physicists were set on the path to quantizing the electromagnetic field itself.
This process of quantization followed the development of quantum mechanics and quantum field theory through the mid-20th century. Through quantization,
The electromagnetic field is broken down into countless modes of all different frequencies. In this new description, even the empty or vacuum state of the electromagnetic field is made of those modes, made of infinite electromagnetic waves stacked and canceled into nothing. And those virtual modes are made of discrete packets, just as real electromagnetic waves are. The electromagnetic field is made of virtual photons.
In quantum field theory, we describe the quantum electromagnetic force in terms of particles exchanging these virtual photons. They take momentum from one particle and give it to another, causing the push and pull that we see as a smooth electromagnetic force. Photons mediate electromagnetism. Now, there's legitimate debate about whether these virtual photons can be thought of as truly real in the same way that a photon of light is real. But what is unquestionably real is the fact that the electromagnetic field is extremely well described as being made up of quantized chunks.
If we use basically the exact same process to quantize slightly more complicated fields, we get the other quantum forces and their mediating particles. The gluons for the strong force and the W and Z bosons for the weak force all emerge from applying these quantization rules to their respective fields.
It should not be taken lightly that this stuff works so incredibly well. We take a classical field, make some symmetry arguments to guess what other fields might exist, apply quantization rules, and boom, we figure out almost all of the particles and forces that make up our universe. The standard model of particle physics is arguably the most successful theory in all of science. It makes predictions that are accurate to 10 decimal places or more. It's not surprising that physicists would want to envelop gravity and space-time into the explanatory magnificence of quantum field theory.
So how do we proceed with gravity? We need to identify the field we're trying to quantize and then apply the quantization rules just like we did with the other forces. We do know that gravity behaves like electromagnetism in important ways. It has a strength at all points in space. It also supports waves, gravitational waves that travel at the speed of light, which we've now directly detected rippling through space from colliding black holes and neutron stars.
But there are crucial differences. According to general relativity, the gravitational field is not a field on top of space-time like electromagnetism is. Rather, in a very real sense, it is the fabric of space-time itself. This tangling of the field with the stage on which it operates is going to prove problematic, but for now, let's proceed.
Let's get a little more precise. In Einstein's field equations, the field we're interested in is encapsulated in something called the metric tensor. This is a 10-valued object made up of scalars and vectors with a value at every point in space. It's a field, albeit a very complicated one, where the electromagnetic field can be thought of as a thing lying on top of the background grid of space-time. This metric tensor field of general relativity, in a real sense, is the grid of space-time itself.
In electromagnetism, the field changes with respect to the grid. In general relativity, the grid itself changes. This is going to prove complicated, but nonetheless, this grid, this space-time, this metric tensor field is the thing we need to quantize if we want quantum gravity. So let's attempt it. We'll start with an approach that hopefully won't break anything. We're going to treat the gravitational field as a small fluctuation or perturbation to an imaginary flat and static background. We poke flat space-time very lightly and see what comes out. Hopefully, a graviton emerges.
This is a very standard approach in physics called perturbation theory. Rather than completely overhauling our model, we just make a tiny adjustment to what we understand and see what happens. The result is a good approximation to reality, assuming the perturbation is very small. Take electromagnetism, for example. We can understand its quantum behavior by taking account of the exchange of different nudges to the electromagnetic field as represented by the exchange of virtual photons in different ways. For a weak interaction, only the most obvious exchanges matter, like the exchange of a single virtual photon. Stronger interactions require us to account for more complex exchanges, but it all works out beautifully.
When we do this to the gravitational field, everything is, remarkably, also fine. Not only can we do a sort of gentle quantization of a weak gravitational field, we get a glimpse of the quantum of that field that mediates the gravitational force, the graviton. What does it look like? Well, it inherits all of its properties in a pretty non-negotiable way from the field it comes from. It's a massless, spin-2 boson. Let's unpack what that means. Massless means it travels at the speed of light, just like the photon. Spin-2 means it has a 180-degree rotational symmetry that reflects the sort of stretch-squish action on space, just like the gravitational waves that should be built from these gravitons. And boson means you can stack infinite gravitons together to make gravitational waves. Just as virtual photons make the quantum electromagnetic field, we can build the fabric of space-time out of virtual gravitons. In a sense, we just succeeded in quantizing gravity. This approach of perturbative quantum gravity actually works. We can use it to recover classical gravity. We can even use it to make predictions, like Stephen Hawking's famous prediction of Hawking radiation. The idea that black holes aren't completely black, but slowly leak particles and eventually evaporate. So why don't we just stitch this quantum gravity to the rest of quantum field theory and say we have a theory of everything? Why not add the graviton to the standard model library and move on with our lives?
Not so fast. We want our final theory to explain the whole universe, but our perturbative quantum gravity only works in the case of very weak gravity. It doesn't work for places with extreme space-time curvature, like the centers of black holes or the Big Bang. We also want to actually verify our quantum gravity theory with experiments, and our perturbative theory works only in situations where it's essentially impossible to differentiate it from regular Einsteinian gravity with any human-buildable experiment.
We really need the full theory. So to finish the job of quantizing gravity, we have to see if we can generalize this to a theory that works everywhere, including where gravity is extreme. As gravity gets stronger, our perturbations get bigger, and the corrections we need to make to our classical theory get larger. More technically, we need higher-order corrections, represented by more complex interactions via virtual gravitons.
Remember how we do this for quantum electromagnetic interactions? We calculate our quantum electromagnetic force by summing over all the possible virtual interactions that could have occurred. For weak electromagnetic fields, it's enough to include only the most probable such interactions, and that means the simplest ones, like the exchange of a virtual photon or two. For stronger electromagnetic fields, more complex interactions become important. That includes so-called self-energy terms, which result from the feedback between the different fields.
These higher-order terms involve loops that appear in the many Feynman diagrams that we sum together to compute a strong interaction. These loops have a notorious property. They seem to generate infinities. In a previous exploration of quantum field theory, we encountered how these loops appear to make quantities like the mass of the electron infinite. But these sorts of infinities can't be real, or we wouldn't have a universe.
In regular quantum field theory, we have a way to remove them, called renormalization. It lets us sort of divide them out by grounding them in measured values, for example, by measuring the true mass of the electron. This is possible with the regular quantum fields because the perturbative expansion, the sum of Feynman diagrams, only generates a finite number of infinities. It's still possible to absorb these into a finite number of additional terms in our equations.
Even if absorbing infinities sounds a bit questionable, it works incredibly well.
By grounding our otherwise infinite predictions in a few finite measurements of the real universe, quantum field theory is able to make stunningly precise predictions of many, many things. Not a bad trade-off. Depicting the electromagnetic field as being made of virtual photons is incredibly successful, which forces us to take seriously this picture of a quantized field. At some level, we believe that the electromagnetic and other quantum forces are mediated by particles.
If we can do for gravity what we just did for electromagnetism, then we can make the same argument for the reality of the graviton. So we're ramping up the strength of our quantum gravity, increasing the complexity of our perturbative approximation, and hoping we can renormalize any infinities to get a sensible theory. And this is where everything goes catastrophically wrong.
The problem is that gravitons interact gravitationally. They interact with themselves. The photon, on the other hand, does not interact electromagnetically, at least not directly. It interacts with, say, the electron field, which feeds back on the electromagnetic field. That extra step limits the complexity of the photon self-interaction and limits the number of self-energy loops, making renormalization possible.
But a graviton can directly spawn other virtual gravitons, which can spawn more virtual gravitons ad infinitum. Instead of a finite number of self-energy loops, we get an infinite number of terms in our perturbative approximation that can't be renormalized, can't be canceled out with a finite number of real measurements. In cases of strong gravity, our quantum gravity theory becomes meaningless. We say that perturbative quantum gravity is non-renormalizable. We can also think of this in terms of the strength of the gravitational coupling, the gravitational constant, getting stronger as the field gets stronger, ultimately sending the field strength to infinity.
This straightforward approach to quantizing gravity leads to nonsense. So maybe it follows that we can't build the gravitational field out of gravitons after all.
Does this mean that the graviton doesn't exist? Not necessarily. What it means is that this simple picture of quantum gravity that we get by applying the same quantization methods as the other forces isn't right. There may be a theory of quantum gravity that just can't be reached by the simple perturbative approach. Interestingly, it's the graviton itself that may lead us to the final answer. Even though the standard approach didn't get us all the way, the picture of the graviton we got from it is almost certainly right. If the graviton exists at all, it has to be a massless spin-2 boson. Nothing else can generate Einstein's field equations in the classical limit.
And that's why, when we find a theory that predicts a massless spin-2 boson, our ears perk up and we wonder if we found a potential theory of quantum gravity. That happened with string theory, which was originally meant to be a theory for quark interactions, but produced a graviton-like particle in such a profound way that it sparked a many-decade quest to find a stringy theory of everything. You can't avoid the graviton in string theory, and in string theory you also avoid the rampant infinities, because at the smallest scales, where gravity can be strongest, the graviton field is smeared out over the vibrating strings at the theory's core.
There are other approaches to quantum gravity, like loop quantum gravity and others. All of them have a graviton, because without the graviton, there's no path to classical gravity. It's again sounding like the graviton is inevitable. But again, no, it's only inevitable if gravity is fundamentally quantum in the first place, if the final theory looks more like quantum mechanics than general relativity.
What's the alternative? It's that the fabric of space-time doesn't have discrete chunks. It's not made of gravitons. Maybe a smooth, continuous space-time is fundamental in some way. A number of theories favor this option. Even Roger Penrose, one of the giants of general relativity, is a proponent of this view, encouraging us to gravitize the quantum rather than quantizing gravity. Fit quantum mechanics into general relativity rather than the other way around.
Ultimately, finding evidence of the actual existence of the graviton will be critical to confirming the quantum nature of gravity
And even determining which quantum gravity theory we have, that's going to be really, really hard to do directly because we'd need to build solar system-sized particle accelerators. Fortunately, there are brilliant methods to observe the indirect effects of the interactions of a quantum graviton that we can pursue now. For example, spotting the mediation of quantum entanglement by a gravitational field, or performing a Cavendish experiment but with exceptionally tiny masses.
One of these methods may succeed very soon, or we may have to start astro-engineering our megacollider. Nature has set a last gigantic hurdle to understanding her deepest laws. We need to understand and then find the graviton. And then we'll hold in our hands the building block of space-time itself. The question remains, are we chasing the right ghost? Or has the greatest physics hunt of the century been following a beautiful illusion? Only experiment will tell.